Okay, let's look at this case here where we're going to find the moment of inertia, and we have to do the integral. So y squared is 400x. The moment of inertia about the x-axis would be y squared, and we'll integrate it with respect to y. The trick is that we need to find this width right here. So that's 100 millimeters minus x. Well, x is y squared over 400. That's the width of this area. So width dA, 100 minus y, there it is, right there, y squared dA. There. So this is the dA part, right there, y squared, integrated from 0 to 200 millimeters. And does that make sense? Y squared equals 400x, which gives 4 times 10 to the fourth, and the square root of that is 2 times 10 squared, so 200 millimeters. So the formula works out okay. And, well, then you just crunch the integrals. Crunch the integrals, and you get this. Number crunching, tedious math. Now you can do it the other way too. So in this case, we're finding the center of mass of this guy, and we got to use the parallel axis theorem to go back to this x-axis. So the center of mass of this differential area is at y over 2, and we find the moment of inertia at y over 2 of this little rectangular area. We already know it. We calculated it earlier, this 1/3 business. And then we have to do this right here. Okay, so it looks a little more complicated. We should get the same result at the end. There, we got that. And then integrate it. There's that 1/3 y cubed dx right there. 0 to 100 in this case, since we're going dx. And we got to do this 3/2 power, and we get the same answer. So the rest of it's tedious math. Y is equal to 400x, the square root of 400x, and then you take y cubed. So that's where the 3/2 power comes in. Okay, now the problem is to find the moment of inertia of a disk right here, Ix, Iy, and then I naught, or J naught, excuse me. So there's a couple things to look at. This distance right here, x, is given by this. Ix then would be the integral from y equals -a to +a, y squared, dA. Well, dA is 2x dy, like that. And then we can get x in terms of y right here. So let's go to the next slide. And voila, we did it. We did it. Go look it up in a table of integrals. Don't do the integral yourself. Let somebody else take care of the tedious math. Okay, now that we have Ix is pi a to the fourth over 4, what is it about the y-axis? Wouldn't you expect it to be the same? And this just looks at a different way of integrating it. Remember how we took the slice like so, and we went up? This is similar to doing the rectangle the same way, and we have to find the center of mass of this guy, and then the moment of inertia about this point, and use the parallel axis theorem and all that stuff. Anyway, yeah, here's the rectangle right here. So, and then we integrate it and we get the same answer. So, in both cases, solution 1, the easy way, is not as hard. So, do it the easy way. Whatever problem you're working on, take a look at it. Try to analyze. Well, gee, what's the easy way to go about this? And that's what a lot of statics is about, is giving you tips and tricks to find the easy way. Okay, composite bodies. What if you have something that is made up of triangles and squares and circles and all sorts of things? So, we've worked out a few of the simple geometries of their moments of inertia. Complicated shapes made up of several different things, easy. You just find the moment of inertia of each one and they add. But, kind of like our prior integrations, you need to reference it to a common point or a common axis. A common axis. Use the parallel axis theorem, Luke. Okay, so find the moment of inertia of this guy about the x-axis. So we know what this is about the x-axis. X of the rectangle, I'll put a subscript r, is going to equal, what was it, 1/3? And that would be the width, call it b. I'll leave it in formulas. And h is the total height, bh cubed. Plus, now we have to use the parallel axis, or, scratch, negative. We're taking the circle out of the middle. So we subtract away that moment of inertia, and I'll call this R. And the moment of inertia is pi r squared over 4, as you'll recall from previously. Now, we have to use the parallel axis theorem. So it's h over 2 squared times its area, pi r squared. That's the total area, h over 2 times 5 squared, plus pi r squared over 4. And do I have that right? Should it be pi r to the 4th over 4? I think it's pi r to the 4th over 4. I think I just remembered the formula incorrectly. Pi r squared is obviously, oh, this one was pi r squared. That's right. This one was pi r squared because it's an area. So I had to leave the 2 alone here. But this is pi r to the 4th over 4 because this is a moment of inertia about the center of mass plus the distance squared to the center of mass times the area. Okay, and let's move on. If I got that right. So 1/4 pi r to the fourth, that's the moment of inertia about the center mass of the circle. And we're talking about the circle only at this time, plus pi r squared, that's the area, times the distance squared to d squared, dy squared. Okay, and you get this number. And I left it in formulas earlier. 1/12 bh cubed, that's Ix about the center of mass of the rectangle. Check your inside back cover. On my Canvas site, I left some other helps too. Other reference helps, lookup tables for these kinds of things. Use them. Don't do it the hard way. Now we need to find the center of mass or the moment of inertia of the rectangle. So we get the moment of inertia around the center of mass plus the area times the distance the center of mass is from the axis that we're revolving around. And that would be the y distance. X is the axis. And d sub y is 75 millimeters, if you'll recall from the previous slides. So Ix will be 1/12 bh cubed. That's what this term is. Area 100 times 150 times 75 squared. That's dy squared. And to get the total moment, you got to take the moment of the rectangle, subtract the moment of the circle that we found earlier. And that's it.